So in the previous week, we saw digital signals, discrete time signals, discrete time systems, and different types of properties of discrete time systems like linear time invariant systems and their properties, convolution and its properties. So now in this week, we will be focusing on periodic signals, and we will be going into Fourier transforms. But let's start with the basics. What is a periodic signal? A periodic signal, so since we are looking at discrete time signals, a periodic signal is a discrete time signal, means the time axis is discretized, and we have, this is a sinusoidal signal, right? It's a periodic signal because the same pattern repeats over time. Can you tell me what is the time period of this periodic signal? So how do you find that? So this is my entry, and this is the same thing. So everything starts repeating from here, and if this is at t equal to 0, this is at t equal to 10. So what is the time period? The time period is 10. And how do you represent this signal? This signal should be something like xn of sine 2 pi fn. Now what is this f? This f is equal to 1 upon time period, which means equal to 1 upon 10. Now you can verify that at n equal to 0, your xn is sine 2 pi 0 by 10, and at n equal to 10, it will become x10 is equal to sine 2 pi by 10 into 10, which is equal to sine of 2 pi, which is again 0. Right? So in this way, you can see the periodicity, the period of this periodic signal is 10. Now let us look at this one. So what is this? This is not a simple sinusoid, but several sinusoids mixed together linearly. This is at t equal to 0, and the same pattern repeats from t equal to 10. So this means my time period is 10. Actually, it will be better if we represent this by capital N. So my capital N is 10. Now, what is the fundamental frequency of a signal? So if we consider any signal, the fundamental frequency f naught is basically 1 upon n, right? And n is the time period, and period in samples. I can convert this, if I know the sampling rate fs, I can convert these things into continuous time frequency in hertz, in samples per second, right? But let's focus only on the discrete time signals for the time being. So tell me, what is the fundamental frequency of this signal now? So very easy, the same pattern, it starts repeating from here. What is the time period here? Is 16. So my capital N is 16, right? It's the 0, and this is 16. Okay. Now, how do we find out? Given a signal, yes, visually I can do the inspection and find out the time period. But if I give you a signal and I ask you to automatically compute, let's say in a program, write a function, let's say in a Python, define, estimate n, and the input is the signal xn and other things. How do you find out the time period? Okay, so what we see is to find out time period, it is useful to do the it is useful to look at this figure. Let's say this is a signal. Now, how do I find out the time period? I will just move this signal and compare it with itself. And wherever it finds a match, the best match, I will say that is the pattern repeating, right? So this same pattern, when I move it, it will match with this one. So this pattern matches very nicely with this one, right? So this is how I find out the fundamental frequency of a signal. I move it and compare it with itself. Self-similarity, when you add the delay to the signal. Now, okay, let's go back to the basics. How do we find out the similarity or the self-similarity? First, we have to define a space. Space is that which provides support and distinct identity to every object. Let us look at some measures of this similarity. One measure could be a dot product, right? You know, you have a vector x, let's say x is a vector, and if you do x transpose x, this is a large value, but if I want to compare, let's say x1 with x2, then this will give me a similarity measure, right? The similarity is measured by dot product. In terms of signals, this is simply xn and yn. These are two signals, and I just take a dot product, which means I take a sum over their element-wise product. That is the that is a measure of similarity. Now, I can measure similarity across time because that's what we are interested in, right? We have one signal and we have another signal, which is a time delayed version of same thing, or it could be another signal, but that they are not synchronized exactly, right? So I'm interested in seeing at what delay this will match perfectly, right? So that's why this delay term has been added. So instead of just taking a dot product, I'm taking dot product with the delayed version of the other signal. So then my correlation is a function of this delay L, right? So earlier it was a scalar, but now it's a vector because I'm checking at every possible value of L. I compare here, then I compare at another L, at another L. So in this way I compare my X and Y. And wherever I get the maximum value of Rxy, so maximum value of Rxy is my best match or the best similarity. Now X and Y are same, so if I take the same signal, as you remember from our problem, we want to find out the periodicity of a signal, right? So if I compare the signal with itself, that is called autocorrelation. So what is autocorrelation? X compared with X, but the delayed version of it. So that is called the autocorrelation function. Let us compute the autocorrelation function for the signal which we just saw in the previous slides. So we had this function, and I have taken a longer version so that you can clearly see the effect. If I operate with autocorrelation function, what do I get? So when the delay is 0, it compares perfectly with itself. So the autocorrelation is maximum here at L equal to 0, right? This is maximum because the delay is 0. It's just a dot product with itself. But now as I start shifting this signal, the other part of the signal, then the match decreases. It decreases, and finally when this peak reaches this peak, then you get this, right? Because this peak matches this peak, then you get this height. But then when you go further and this peak matches this peak, then you get this, and that happens at the periodicity of the signal, right? If you notice these points, so here you get another peak. If you notice, this is at 16. So what is the time period of the signal? Time period, or capital N, okay, is equal to 16. And what is the fundamental frequency? F naught is 1 upon 16. Okay, and then I go further, because you know this periodicity is a long range periodicity. So if I go further, again the same pattern will repeat. I get this peak, right, at 32. So in this way I can see how to find periodicity using the autocorrelation function. Now the question is, why this is reducing in amplitude? Whenever it matches itself, why is it reducing? How to avoid the peaks decaying with L? It is reducing because the sum, the number of samples over which you are summing, that is reducing, right? When you are doing here, you're just summing from this point to this point because you simply don't have other values available with you. So if you look at the formula, then you see here it is going from 0 to n minus L minus n minus 1 minus L. Sorry, it should be n minus L minus 1. Simply because I don't have other values. Now, next thing is, how do I take care of this bias now? So if I simply divide this term with n minus L, then I take care of that problem. If I simply divide this with n minus L, then what do I get? I get all my peaks are now at similar height, right? Because yes, I'm now adding over a smaller length, but if I normalize with this length, this is n minus L, if I normalize with this length, then they are comparable. This is the unbiased short-term autocorrelation. Another measure of similarity is squared difference. I can use squared difference to find similarity between two vectors. Let's say if I have vector x and if I have vector y, I want to see if these two vectors are same or not. What can I do? I can take the squared difference, right, which is equivalent to norm of x minus y vector whole square. And if you write it in terms of elements, then this is what it becomes. This should be L minus 1. Xn minus xn plus L whole square, the delayed version, because your y is just the delayed version of x, and this is your difference function. Now, if I plot this difference function with respect to the delay L, what do you expect? This is my original signal. You can see the periodicity is 16. Here, capital N is 16. And what do you find here? When you are comparing the same signal with itself, the difference will be exactly 0 because it is the same signal. Now, if I keep moving, I move this and I reach here somewhere like this. And then you find that I'm sorry, it should have been further here. When this peak reaches this one, then you find that at this match you get a minimum here, right? And then again it increases. So at this it will be a maximum because you are cancelling. You are reinforcing the difference is more. So you get a peak, but here you get a trough because the similarity is more. Now if you move the complete cycle, which means you again reach capital N, you find another trough, another valley, or a minimum here. So this is at 16. This was at 0, and this is at 16. So you will find the minima at capital N. This is another way to compute the similarity between two signals, and in this way to compute the periodicity of a signal. Okay, so summarizing what we saw in this video, we looked at periodic signals, We looked at different ways to estimate the time period, capital N, of the signal. We, in particular, autocorrelation, both biased as well as unbiased, and squared difference. But these only estimate the fundamental frequency of the signal. How to estimate all the frequencies present in the signal? If I want to know, let's say there is a frequency of n equal to 16 or n equal to 32, like that. So what all frequencies are present in the signal? How do I find out that? So for that, we have to go to the Fourier analysis, which will be the next topic in our lectures. Thank you very much.